Hello. Today we are going to present our project Multi-Agent Motion Planning for Non-Holonomic Mobile Robots via Heuristic Optimization. The team members are Vishrut Bohara, Vinayak Gaikwad, and Aadesh Varude. The research problem and the description statement is defined as below. We aim to propose a motion planning approach that generates a safe, dynamically feasible, and near optimal trajectory for multiple non-holonomic robots. The main contributions of our work are implementing a multi-robot motion planner to generate initial solutions, trajectory optimization considering collision avoidance heuristics. The application impacts of this project could be defined in three various areas. First is the warehouse. In the warehouse, multi-agent path planning could help in various task coordinations efficiently. Surveillance. Multi-agent path planning is used in surveillance to coordinate the movement of multiple drones or other surveillance devices, ensuring that they cover the area of interest without overlap and that they collect the necessary data efficiently. Rescue and search operations. In search and rescue operations, multi-agent path planning can be used to coordinate the movement of multiple search and rescue robots, allowing them to cover more ground and find the survivors faster. Further, now we will gather some literature review that is required for our project. In this slide, we look at our major focus paper, that is the efficient trajectory planning for multiple non-holonomic robots via prioritized trajectory optimization. In this paper, the author presents the idea of multiple robot path planning via trajectory optimization in non-holonomic constraints. The author proposes new methods for trajectory planning in obstacle-rich environments. They provide exhaustive simulation and real-world experimental results to prove the efficiency of the algorithm, as you can see in the image in the left-hand side. Further, the author decomposes the algorithm into three folds. First, the author implements a priority-based, enhanced conflict-based search algorithm to generate trajectories which are collision-free for multiple agents. And the second step for this is a generation of a safety corridor passage for each and every agent in order to ensure safe distances from the obstacles and the agents. Finally, the trajectories are smoothened and optimized using an MPC-based optimizer. Further, the testing is done on multiple agents to give the experimental results, as you can see on the left-hand side of the PPT. Further, we dive deeper into the conflict-based search as it being the crucial part of our approach. So here is the paper, Suboptimal Variants of Conflict-Based Search Algorithm for the Multi-Agent Pathfinding Problem. In this paper, we essentially come across three major conflict-based variants. First, the greedy conflict-based variant. The GCBS algorithm employs the same framework as CBS but offers a greater flexibility in both high-level and low-level search problems for multi-agent pathfinding. Further, we have the BCBS, that is Bounded Suboptimal Conflict-Based Search. In this variant applies a focal search to both levels of CBS using different heuristics. And at the end, we have the Enhanced Conflict-Based Search algorithm that generates a CT node, and a low-level search returns two values to the high-level search and the cost of the node and the minimum lower bound of all the nodes in the open list of the high-level search. Essentially, the bounded suboptimal CBS and the ECBS perform almost similar, but the major advantage of the ECBS over BCBS is being the two return outputs that are returned to the high-level search, which actually reduce the computational cost of the high-level search.
The second most important component of the state-of-the-art implementation is optimization and smoothing methods. For this, we have explored various papers, and one of them is path planning based on Bezier curve for autonomous ground vehicles. In this paper, authors present Bezier curve technique for generating smooth and feasible trajectories for autonomous ground vehicles. First, a path is formed doing a grid-based search method, and later it is smoothened using the curve fitting algorithm. The path planning in Bezier curve technique is done using two methods. First, path planning based on Bezier curves with each line segments. In this method, between two nodes, a line segment is formed, and on each given line segments, the Bezier curve fitting algorithm is implemented to find the smooth trajectory. The second method is placing the midpoints of Bezier curve on bisectors or turns. This is useful for sharp corners or edges to generate a smooth curvature for non-holonomic mobile robots. The second paper which we gone through for optimization and smoothing methods is an efficient B-spline based kinodynamic replanning framework for quad rotors. This paper provides an overview of kinodynamic planning for quad rotors, which involves planning dynamically feasible motion. The authors have used a B-spline technique, which is different as discussed in the Bezier curve technique, which generates smooth trajectories for kinodynamic planning. The algorithms here are evaluated using a drone as a testing method on monocular vision test bed in both indoor as well as outdoor environments. The images on the left-hand side show the pictorial representation of experiments conducted in indoor and outdoor environments, where we can see smooth and optimal trajectories. The B-spline technique uses a piecewise polynomial function which is used to generate a complex path. This method is more efficient than a generalized trajectory optimization method as it can efficiently plan paths in sharp turns or curves, which is ideal for drone navigation. This algorithm uses an elastic optimization approach, and the results for the same are shown in the left image, which you can see. The original tube here in the image is marked in green, while the inflated tube is marked in yellow. The illustration of the EO approach represents both the elastic expansion process and optimization process. As you can see, the EO approach works perfectly fine in more cluttered and obstacle-based environments and gives smooth trajectories.
When we were looking for the optimization-based algorithms, we came across this paper which solves the similar problem in a completely different application scenario. The proposed method first calculates a path using RRT algorithm, which is then optimized using a line-of-sight control checking algorithm. The author also proves that that the algorithm returns a homotopy optimal path. This paper was interesting because the algorithm presented is less expensive in terms of computation and can easily be scaled up for multi-agent systems. Moving on to the proposed approach, we divide our algorithm into three main components. First, we use a ECBS method with a A-star planner to calculate collision-free trajectories. Then in the next step, these generated trajectories are passed through a heuristic-based improviser to get optimal trajectories. Now, as we have the optimal trajectories, we finally pass it through an optimizer, which convert these paths into known holonomic feasible paths so that it can be used on multi-agent mobile robots. Following our proposed method, this is what we have implemented till now. We started with the ECBS based planner implementation following the state of the art algorithm. So like our current implementation is basically a combination of the state of the art with the line of sight algorithm. We implemented the ECBS based planner first. Then we looked at the optimization methods. The state of the art uses MPC based optimizers, which is very computationally expensive. And we wanted a scalable and faster algorithm. Therefore, we shifted to the line of sight algorithm, which was used in DT-RRT literature. Although this line of sight algorithm sometimes is only returning homotopy optimal paths, but based on our analysis, the trade-off between the homotopy optimal path and the actual optimal path is not that significant, as the path generated is coming from ECBS algorithm. On the right hand side, you can see a very brief pseudocode for our implementation till now. And just to brief, the starting in in the first step, we calculate ECBS A star path for all the robots, which are then passed through line of sight path to calculate the non-holonomic optimal path using line of sight algorithm. And these are saved into our computed paths, which are then used in calculating conflicts for other multi-agent robots.
The following slide shows our results in a custom visualizer. Here you can see objects in black and the white is the free spaces. We have put the start and goal positions for each of our robots, and we can observe that the robots are following their individual paths without colliding with any obstacles and any other agents around them. This is our gazebo simulation setup. Here we have created a custom world with 3 turtle bots, and we aim to test our algorithm in this setup. The following table represents the timeline and work distribution among the team. Currently we are on week 5 and we have benchmark this week. In this week we are doing our proposal slides, video and reports. Thank you so much for hearing us.